And hi, class. And this is the first class we talk about some numerical methods, some actual numerical methods things in this class. So let's see. So this is chapter 5, and it's about the computer arithmetic. The first lesson we're going to talk about today is the floating point numbers or representation. Wow, what's that? Oh, on a moment. Okay, let's just go back. Let's have this one. Okay, and so we have the floating point numbers, and then in the usually we use the scientific notations with base 10 represents the number as a factor multiplied by a power of 10. So for example, we represent this number 356100000 with. So a lot of time, if we want to use a scientific notation, and then we just extract the significant number here, and then the significant number is the 3.56. And we use it and then multiply it fetch a power of 10, and then here we have the power of 10 and then to the order 6. And you don't need to take all the notes because I will post the notes to the Canvas. And here we have a binary scientific notation, and instead of the base 10, and then we have the binary scientific notation, and it's in this following format. So for any real non-zero number, we can represent the x in this way. So there are several components here. So the first component is the signs, because we have negative number, we have positive number. So we have the first part is the sign. And say similar to the 10 bases, we have the significant S. And then we also have the power of, instead of a power of 10, because this is a binary scientific notation, we have the base 10, base 2 here, and then this is the exponent. And so there are three parts here, signs, significant, and the exponent. And here we have in their 10 base representations, we usually require that this number is smaller than 10. And here we require that this significant is smaller than 2, but it is bigger than or equals to 1. So if we represent also this S number should be usually represented as to the binary format. And then in the binary format, it should be if the number S is between the 1 and 2, the binary format, I'm using this subscript here, 2 here, to represent this is the binary representation. And the number in between this can be represented by 1 point B1, B2, and so on and so forth here. And then the B1, B2, the BI number should be 0 or 1. And this is the binary representations for the scientific binary representations for one number. Any questions here? A brief introduction. So it's quite similar to what you have done for the 10 bases. But here we change it to the binary one, and then we have the signs, we have the significant, and we have the exponent. Okay, so let's see. So usually the computers, we have 2 precisions, and so we have the single precision, and we usually store the numbers in bits, and that is the numbers, the bits usually store 0 or 1 in the computer. And for the single precision, and then we have 32 bits in the computer. And if you have double precisions, and then How many bits do we have? We have 64 bits in the computer. So let's see. Here we have representation binary scientific notations for the real number and any real zero number here. And let's see what would we have in the computer story. So there's one question here. How the computer store the numbers. With double precisions. So we just list the double precisions for example, and then how the computer store the numbers here. So let's just do some copy and paste here first. So this is the binary scientific format, and actually in the computer would use just one bit. So here we have 64 bits, and here we would use in the computer, it would use one bit to store the sign information. And for the significant, we have 52 bits for the significance. And by default, the base is 2, right? And then for the E, the number E, and then we have 11 bits to store the information for the exponent. And this is how the computer distribute the bit for the number storage. And this is the double precision for example. Any questions here? Okay, so if you don't have any questions, then let's see the next things. So if we have double precisions and we only have 64 bits, and this means that there are finite floating point numbers in the computer. So how can we compute the range that the double precisions can represent? So let's see the double precisions. Let's take a look at the exponent first. So we have 11 bits, and then for each bit, we can have either a 0 or 1. So here, the maximum number it can represent, the maximum exponent it can represent, it should be, because for each bit, we have 2 choices, right? And from the combinatorial knowledge, we know that you can represent the maximum number you can represent, it should be 2 to the power of 11, because for each bit you can have 2 options, right? So here we have 2 to the 11, and this number equals to 2048. But actually in the computer, the maximums or the minimum of the exponent should be this. So let's shift the number a little bit, and I shift the 2048 a little bit to the negative axis, and then we get the negative number. And but there's something happening in the computer, and then you can look up in with the ChatGPT. ChatGPT will tell you the answer. That's a very complicated reasons inside it, but there are 2 numbers of 3 numbers is not calculated here. It's using to store some other informations, maybe the sign informations here. So, but the minimum exponents we have in the actual computer should be, for the double precisions, should be the -1022, and the exponent, the maximums of the exponent should be the 1023. So this is some information for the exponent. And what about, so we have the positive and negative sign here, and we also have the significant. So if we want to look into the range, we also need to pay attention to the significant. So here we are talking about the range, but we are saying the absolute value, the minimum of the absolute value and the maximum of the absolute value, because you can just change the sign to get the positive and negative, right? So here we are just talking about the minimum of the absolute value. So let's see how to calculate the smallest number double precisions can be represented by the computer. So let's see, here we are going to calculate this number. And we are just calculating the minimum of the absolute value number. So the number minimums, the smallest number double precisions can be represented. That is just say absolute value. And it should be the 2 and then to the minimum of the exponent here. And that's the 2 to the power of negative 1022. This is because if you take a look at the S number here, and then the S number is 1 point B1, B2, and then B3, and so on and so forth. And this number is just the if you go to take a look at the binary representation, and if we have a 0 here, and then it represents 0 times to 0, and this is the first place, and 1 here, and then it should be 0 1 times 1 times 2 0. And if we have a binary representation, it looks like this: 1 0, and then what is the 10 base number? So here is just 0, and this is just 1. And if you have a binary representation here, it's 1 0, and then what is the 10 base number? It is, so for here we have starting from here, it should be the power of 0, and then this should be the power of 1. So if you want to calculate the 10 base number, and then what do we have? We have 0 times the 2 0, and then 1 times the 2 0, and it's just 2. And this is how we calculate the binary number. Translate the binary number to the 10 basis one. So here is the 10 base number, 10 base number, 10 base number. And but now you have a point here, right? And then how can we calculate it? It doesn't matter, right? And then it's just, this is for 0, power 0. And then this is for power -1, -2, -3. So what's the number here? It's just the, okay, it's just the 1 times the 2 0, and then B1 times the 2 -1, and then B2 times the 2 -2, and B3 times the 2 -3, and so on and so forth. And so because the B1, B2, B3, they are they are 0 or 1. So this number could be, the smallest number it represents could be just 1, right? And then we just take the B1, B2, B3, B4, all the BI here to be 0. And this is the smallest numbers S can represent, that is just 1. And so here, the N minimum number is the S minimum. So let me just write it again. This is just the S minimum times the 2 E minimum. And this is the 1 times the 2, and then this is 10 basis. The 1 is just the 10 basis 1. And this is the number 2 to the 1022. And so this is the minimum number. We can represent the minimum of the absolute value of the number here. For the double precisions, it should be the 2 to the -1022. So this is just the smallest numbers. And then what about the largest number? Any idea here? So we take the 2 to the power of E minimum, right? Exponential minimum. So if we want to calculate the max number, it could represent. So there's a significant here. and then times the 2 E max. And what about the S here? How can we take it to be the largest one as possible? So the S significant, it is represented in this way, right? 1 point B1, B2, B3, and so on and so forth. And there are 52 bits here because this is a double precisions. We have 52 bits. And how can you take the maximums of numbers here? So consider, let's take this into account. The B1, the 1 point B1, B2, B3, and then in the binary format can be translated into these 10 base numbers. So if you want to choose the maximum number, what would you choose for the BI? All ones, right? Because you have 1 here, you have 1 here, and then you can make the numbers to be the possible maximum. So here we just take the S to be all ones. So we have 1.111 and then to the 1, and we actually have 52 ones, and then up to the point, the decimal point. So we are going to calculate this number, and by the binary operation, you would know that if you add, so I'm going to do some translation here. So if this is the 52 bits number, right? 1.11 and then all the ones here. And then I'm going to add the 0.11, 000, and then at the end I have a 1. So all these are binary representation. If I do the sum, and then what can I get? So in the binary operation, if you have 1 plus 1, and then it gets 2, right? But in the representations, we only have 1 and 2. So you can just have represents here. Okay, I get one more 1 here, and then to show you the operation. So 1 plus 1 is 2, but we replace the 2 with 0 here, but we add 1 in from top in the previous space here. And here we have 1 plus 0 and then plus 1, and then again 1 plus 1 is 2, and then we have 0 here, replace it with 0, and then add a small 1 here in the previous space. And then so we have 1 plus 0 plus 1, and then once again this is 0. And if you do this operation, and then what can you get at the end is, okay, here we still have a small 1 here for the previous space, and then this is 1 plus 1, and then replace it with a 0, and then there's 1 here in the extra space here, and then so this is the results, 1 0 and then 0 0 0 0 0, and then it is a binary representation. And this also means that this number it equals to 1 0 and then 0.0000, and that's 0 2, and there are 52 0 here. And subtract the 0.0001, and this is the 52 decimal point after the 52 point space after the decimal point. And this is the, because we do the sum here, this this one equals to this one. So now we have this one subtract this one equals to this one. Does it make sense? So this is the easy ways we can calculate this number. And times the 2 E maximum. The E maximum here is 1023. We just calculate this one there, the E maximum. So we shift it a little bit, and then with some complicated computer knowledge, and then you know that there are 3 numbers are missing, and that complicated knowledge is too complicated to mention in the class, so you can look up in the ChatGPT, and it gives you the true answer. But it's not it's not something about the mathematics, so I'm not going to mention this in this class. So let's go back to take a look at the maximum numbers it can represent in the computer. So this number, if you take a look at here, what do we have? So we need to calculate this number. And this time we have all the zeros after the decimal point, and then so this part is just a 0. And this one is the 1. And then times the 2. And what is the space here? The space here is it represents the power of 1. And this one represents the power of 2, 0, 0. So here we have just the 0 times the here. And this is the 10 base number. So this is 2 per 0, and then it is just 2. To subtract, and what is the things here we have? Behind the decimal points, this is behind the decimal point, 52 places. So here we have, this should be, if you calculate the 10 base number, and then it should be 2 to the negative 52, and this is the 10 base number, and then times the 1, the 2 to the 1023. And this number, you can do a little bit computations in the computer, and at the end, it's approximately equals to the 1.8 times the 10 bases. This is the 10 base representation here. If I don't use the subscript 2 here, and then all the things should be 10 base, okay? And this is the maximum possible numbers. It could be represented by the double precisions, and that is the smallest absolute value numbers that can be represented by the double precisions. Any questions here? No questions? Well, that's a happy class. Yeah, you would go through this class, looks like this. Every time, no questions, because it's not too difficult. If it's too difficult, and then raise your hand. Okay, the next part, we are similar to the 10 bases. So let's do something to before we go to the binary part. So if you take a look at the 10 base, okay, let's do some rounding up and then rounding down. So for example, 4, 3, 6, 5, 4, 3, and if we want to keep, we only want to keep 3 decimal points up to the decimal. We only want to keep 3 decimal digits. And then with the rounding up, rounding down, and then what is the number? Could you tell me if you want to just keep the 3 decimal digits, and then what will you keep here? Doing the rounding up, rounding down, 3.654, right? Okay, good. And so if we do this, and then this is another number, and then this is another number, but once again, we want to keep 3 decimal digits, and then what is the approximations? We need to round up because this number. So how would you decide this one? So it should be 655. And how do we decide this? So it depends on the numbers up to that digits. We only want to keep the 3 decimal digits, right? And then after the 3rd digits, that is the 4 digits, it depends on the 4 digits here, the 4 digits here. If the 3 is smaller than 5, and then we just keep the number, just chop it off. And then if the number, the 4th place number here is 6, right? And it's bigger than or equal to 5. And then we can round it out, which means that we add 1 to the 3rd decimal points, right? And this is how we do it. And this is the 10 base. So this is something you already know. And we are going to go back to the, go to the binary one. So to chop their decimal point, the binary numbers, and then we can just do the chopping. And if we want to keep the D bits in the significant, which means that after the D bits, we discard all the numbers. So for example, we have a lot of numbers here, but we only keep the D bits here, the B1, B2, and the BD. And this is the chopping. And for examples, we have these numbers here, 1.011011101, and then there are a lot of numbers coming after that. But there's a significant, this is the exponent, but we are not doing anything about the exponent here because we are just talking about keeping the D bits in the significant. So if we want to keep the 5 bits, and then which means that we only keep 1, 2, 3, 4, 5, and then chop all the things off. And this is the chopping and truncating. And if we want to do the rounding up and rounding down, we are doing some similar things. It looks like this one. If it is smaller than 5, and then if it is bigger than or equals to 5, and there's one criterion here. But in the binary one, in the binary way, and then it's quite easy. You don't have the 5 number. So here, if we want to keep the D bits in the significant, and then you need to log into the D plus 1 bits. If the D plus 1 bit is 0, and then we run it down. And then if the D plus 1 bit is 1, and then we are going to run it up. And this is the binary way. And so let's take a look at one example. We have the same example here, 1.01101. So this is 5 bits, the first 5 bits, right? And we want to do some rounding up, rounding down. So we need to take a look at the 6th bit, and then that's 1. 1, it means that we need to round it up. And then how can we do the round up here? So, so in the binary way, we will add 1 to the previous bit, right? So we would do the similar things to the binary way. So B6, let's see. Rounding up, it means that we are adding the, oh, I have already write out the things. I forget to erase all the things from the previous lesson. Oh, sorry. I shouldn't let you to see the answer so quick. But let's see. So this is the 5 bits here, 01101 here. This is the binary bits here. And then because we are doing the rounding up, because this is 1, and then we are going to do the rounding up. And so we are going to add 1 to this position. So it means that we are going to add 0.00001. So I'm not going to do it in this way. Actually, I'm in my handwritten draft paper, I'm calculating this in this way. And so I am going to, so actually I'm going to do the calculations in this way. And this is the binary, right? And actually I'm skipping some writings on for the 0.00001, but I'm going to just add the 1 there. But actually you can write all the things up. And then I'm going to do the summation, and then the 1 plus 1 again is 2. So I replace the number here with 0, but add the 1 to the 1 place before it. And so I have the 1 here in the second last place. And so I have 0 plus 1, and then this is 1. And for all the things here, we have 1 plus 0 is just 1, 1 plus 0 is 1, 0, and then 1. And this is the results I got. So usually I would just write down this way, not the horizontal way. I would write the vertical way and to do the calculation. And if I have one more 1 plus 1, and then I will put the 1 here and then replace this number with 0. And this is how I do the calculation. And let's see another example here. If this is the numbers I have in record, and then I want to keep the 5 bits for the significant, and then we are going to do some things, rounding up or rounding down. So let's look at the first 5 places. So the first 5 places looks like this, and then 0, 1, 1, 0, 1. And then what is the 6th place? The 6th place is this one. The 6th place is this one. So this is the first 5 one, the first 5 bits, and then this is the 6th bit, and the 6th bit is 0. So we are going to do the rounding down, and doing rounding down is simpler than the rounding up, because we just need to discard all the things after the 5 bits, and then keep the green part here, and then this is the rounding down. Any questions here? It's pretty simple. It just depends on the if we want to keep x bits, and then we are going to look into the x plus 1 bits, and then it depends on whether that x plus 1 bit is 0 or 1. Any questions? Oh, and that's really good. And so so far, we have already talked about the rounding up and rounding down. And there's another way to think about the rounding up and rounding down things. And there's a formula here. This is the rounding of the x. And if we want to keep the d bits, and then we can do this. This is the x number, and then we plus the things with 2 to the negative of d plus 1. And this is actually what we did here. If you take a look at here, that is what we did. That is just the d plus 1 bit number. This is the d plus 1 bit number, but it's in the 10 base representation, and then times the significant, and then top all the things off up to the d bits place. And this is the one formula to think about the rounding up and rounding down. So next, we are going to talk about some things we will talk about throughout the course, because we are doing some numerical methods. Numerical methods is actually, in other words, it's approximations to one true solution. So we need to talk about error, because it is not the true solution, it's approximation. So this is the important topic, error. So a lot of the time when you are doing some, you get some money, right? You get 100. Someone should pay you 100, but he actually give you 97. A lot of the time you just say, you owe me $3. And that is the absolute error. And then we use the solution, let's subtract the approximation's value and getting the absolute value, and then that is the absolute error. But this doesn't make a lot of sense in the mathematics, because a lot of time your value is really small, and maybe you are getting the number 0.000001, and this is the true solution. And if you have a number that is 0.000.2, and then can you say the error is not notched because the error is just 0.00001? Not really. We are not measuring in this way, because maybe all the calculation, all the numbers is in this scale. So if you are calculating the absolute error, and then it doesn't play a very important part in the measure in the measure. But if we want to measure the error here, we can use the relative error. So if you take a look at the relative error here, this is the true solution, right? And this is the approximation. And then what is the relative error here? So let's say this one is just a 10. Let us write it into the scientific notation. This is the 10 to the negative 6, and this is 2, 10, negative 6, negative 6. And if we want to calculate the relative error here, we got this. We got the true solution minus the x subtract the true solution. This is the approximation number, and then divided by the true solution, and then it should be the 10, negative 6, and then 10, negative 6, and then e equals to 1. And this means that we have 100% error, and then this is quite large. So a lot of time, your numbers has the scales, and then you get a lot of approximation, and then they are in the same scale. The absolute error doesn't say anything about how big your error it is. And actually, we are using the relative error to measure how accurate we achieve. So this is the relative error. And sometimes we will use the delta to represent the relative error without the absolute value signs here. And then we use the delta to represent such an, maybe this is the rounding of the x, and maybe this is just the approximations of the x. It could be anything, and then it could be the approximation of the x. But here, if this is the rounding of, or rounding down, the rounding of the x, and then we can represent, so from here, we can represent the rounding of x equals to the x plus the 1 plus delta. And this is one convenient way to represent the rounding of the x with the relative error here. And this is just one way of the representation. And let's go back to take a look at here, this page. So if you take a look at the chopping off there, the chopping of the x, and then you will find out that, okay, this is just a representation, binary representations for the number, right? If you do the chopping, and that error, because you are chopping the, looks like this, 1 point, B1, B2, B3, right? And then BD plus 1, and then BD. There's a sign here, negative or positive, and times the 2e. So if you are doing the chopping, which means that we are chopping off the d plus 1 and the things after it, right? And so the error should be, it should be smaller than this number, 2 to the negative d, and then times the significant, the exponent here, because we are chopping off all the things below up to the d bits. And so the error should be smaller than this one. Any question here? Because this number here, all the things here, it should be the BD plus 1. And then times the 2, negative d plus 1, and then plus the BD2, and then times the negative d2. And if you take all the things to be 1, and then if you do all the sum here, and it should be still smaller than the 2 to the negative d. You have a sum of the series to prove this one. So this number should be smaller than this one, and then you can do some cancellation here. This cancel this one, and this number it should be bigger than or equals to than 1. So this whole number should smaller than or equals to 2 to the negative d. And for the rounding up or rounding down, that is same things as the 10 base 6. And so we only have the half of that digits errors here, because we are doing the rounding up and rounding down. And then if it is going closer to the 1, and then we are going to round up, and then if it's going closer to the 0, and then we are rounding down. So this rounding up error should be 1/2 of the 2 to the negative d. And here we give a name to the 2 to the negative d, and it's called the machine precisions. So in the double precision, dp here represent the double precisions. In the double precisions, we have 52 bits for the, so this number is coming from here. So I just mentioned something about this. So we have for the exponential, no, this is not exponential, this is the significant, because we are talking the precisions on this on the significant. Because if you take a look at here, the exponent is canceling out. So all the things here, it only the error, it only comes from the significant. That is why we call it is significant. So that is because it's significant. All the errors coming from the significant number. So because we have 52 bits to represent the number there. So and the smallest numbers we can represent with that significant. It should be the 2 to the negative 52. I mean the B 0 0 and then all the 0 here, and then the 52 bits here, and this number is equals to this number. And now, so this is the machine precisions for the double precisions. And the smallest double precisions number greater than 1, it should be the 1 plus the machine precisions. And that is the things we just mentioned. We can represent the rounding of the x with in this way. So this means that in the double precisions, we would chop all the things off up to the 52 bits. And this is the machine precisions we have and the double precisions. Any questions so far? So this is double precisions, and I have one question for you. It looks like you don't have any questions. So I have one question for you. And I would like you to go back to take a look, do some search on the internet to see how many bits we use for the sign in the single precisions, how many bits we are going to use for the significant, and then how many bits we are going to use for the exponents in the single precisions. And this is the first question. And the second question is that you need to look with all the information you have for the single precisions. You also need to answer these questions. What is the machine precisions for the single precisions? And that's your homework. You need to look up the information on the internet and then to do some work. So this is the first part, and the next class we are going to do some rounded. So in the computer we need to do some calculation, right? We need to do the sum, we need to do the multiplication, we need to do the division. These are some simple operations in the computer. We are not going to talk about the square root, some cubic root here. We are just going to talk about some simple calculation here, and to see the rounding off errors in the calculation operations here. So in the computers following the IEEE standards, they are calculating the operations in this way. They are going to calculate the correct exact result, and then after it calculates the exact result, it do some rounding off. So for example, we have the summation here. this is the machine additions. And then if we do the machine additions for X and Y number, these are floating point numbers. And in the machine, it's doing in this way. First, doing the summation for X plus Y, and then you get the exact solution. And in the machine, it only has limited floating points, right? 14 numbers. So 14 bits, the bits to store the numbers. So it's going to do some rounding off here. And then so it's going to rounding off the exact number. And so after that, we can do some representation here in mathematics. And this is the exact number. And then 1 plus the rounding off errors here. But this rounding off error should be smaller than the machine precisions. And for the machine precisions, double precisions, that is just a 2 to the negative 52. And that's the things. Here in the next sections, we are going to see if we calculating the rounding off error in this way and one by one, and then to see which operation are good operations, which are not good operations in the computer. And in the next class, you'll find out that the addition, subtractions are the bad ones. And then the multiplication and divisions are the good ones, because it will not enlarge the errors in the calculations. And that's the end of today's class. If you have any questions, you can come here to ask me after the class. Yeah, I would.